All right, we're looking at an optimization problem. This is number 24 from section 4.7. And we're trying to optimize the area of a rectangle inscribed in an ellipse. And so you have an ellipse and you get a rectangle inscribed in there. And specifically, we're trying to maximize. Minimize would be kind of a dumb question because you just, put that top right corner right there, and you'd have a really stupid rectangle with zero height, right? Or you'd put the top right corner right there, and you'd have a really stupid rectangle with zero width. So in fact, that's our relevant domain for this problem. If we're trying to find the area of the rectangle, the domain I'm going to say on the x coordinate of the top right corner, which is something I'm going to talk about in a second, the domain is going to be anywhere from 0 up to this x value right here, the right endpoint of the ellipse, which I guess I should talk for a second about the ellipse itself. That's going to be a, though. I'll just go ahead and say that right now. So the domain is going to be 0 to a. And I like to include the endpoints. Some people would not, because they would argue that if, again, those stupid rectangles I just showed you, which are when x is 0 or when x is a for the top right corner of the rectangle, they would argue those aren't really rectangles. I would argue they are what are called degenerate rectangles. And they're, kind of stupid rectangles, but they, I like to include them because in the concept of absolute extrema, what we're trying to do here is find the absolute max area of this rectangle. And I think it's good to note that the endpoints give you the absolute minimum area, which is 0, and then the absolute max is going to be somewhere in between, by some theorems we've seen and definitions. So with that in mind, first of all, I did mention this, if you don't remember your conic sections that well, that is an ellipse. You can tell because x squared plus y squared, x squared plus y squared equals r squared is a circle. And when all you do is, divide x by a constant and divide y by a constant, you're really taking a circle and you're stretching it, right? You're doing that transformation to it. In fact, you could look at this and see it as the unit circle. And then with these, x over a quantity squared is equivalent to that, right? And y over b quantity squared. And if you look at it that way, now it's that unit circle stretched horizontally by a factor of a and vertically by a factor of b. And so when you think about it that way, that tells you that this point right here, instead of being the 1 on the unit circle, the radius of the unit circle is going to be, it's stretched by a, so that'll be a. And that y coordinate up there will be b. That's how far, those numbers are how far you go from the center of the ellipse along the horizontal and vertical axes to the outside edge of the ellipse. Even if a and b are less than 1, it still works. Then you're kind of like squishing instead of stretching from the unit circle. Still works if you think it through. But I'm not going to talk more about that right now because that's not really the point of this problem. But you do need to know what that ellipse looks like, I think, a little bit at least to understand this part. So I'm going to get rid of my unit circle stuff here. And whoops, that's not what I wanted to do. Here, we'll just do it that way. And yeah, we need to represent the area of this rectangle now, right? That's the thing that we're trying to optimize, right? Maximize the area of the inscribed rectangle. So that's, I need a base and a height, right? I could write area equals length times width or base times height here if I want to. I'm going to take a step off though, because if you do that, then we're going to do a couple relationships here. My advice, if you're inscribing one figure inside of another, and especially if you have an algebraic equation for the figure that you're inscribing into, I would say focus on one key point. And usually I will say the top right vertex. I kind of already mentioned that. So it'll be in the first quadrant. And the advantage of using that is both coordinates will be positive. And all we need really is this point. I'm going to call it x comma y. because that's, that'll be the coordinates, right? X and Y coordinates, since this is the origin. And so if you focus on that point, you can use that X coordinate and that Y coordinate to get the base and the height of your rectangle. If you need to think for a second, pause and think about it. Okay, and yeah, the base of the rectangle is just going to be 2x, right? X plus x, and same idea with the height. It's going to be 2y. All right, and so my area is base height 2x times height. No, I had it right. Base is 2x, height is 2y. I'm struggling here. All right, 4xy. That's the area. That's the point. Okay. So I have that's my primary equation. This is the thing that I am trying to optimize, right? It's good to identify that early on in one of these problems. It's like the first thing you're going for. What is the thing that I want to maximize or minimize? Then you need to ask yourself, how do I get it in terms of one variable, one independent variable? Right now I have x and y. But look around and think, we didn't use the ellipse yet. How do we get rid of one of those? And the ellipse equation up here is how, right? That is an equation that relates x and y for every point on the ellipse itself, and that upper right vertex is on the ellipse because that rectangle is inscribed in it. So that point, x comma y, is on that ellipse. That means it has to fit this equation. So that's what we're going to do. We're going to go ahead and solve this ellipse for y. So I'm going to subtract the x squared over a squared from both sides. And then you could multiply by b squared and x, or take the square root of both sides. I'm going to go ahead and take the square root of both sides. Plus or minus, right? But again, we're in the top right corner, so we're in the first quadrant. So I'm going to disregard the minus and ignore that, just the minus. And we're going to then multiply by the b that's left over. And so we get y equals b times the square root of 1 minus x squared over a squared. Now we have a representation of y in terms of x, that upper right corner y coordinate, in terms of that x coordinate. X is going to be my main independent variable here. So now I can take my primary equation. This here I would call a secondary equation. You use a secondary equation to relate the two variables that are the independent variables in your primary equation, so that you can substitute one in for the other and have your primary equation in terms of one variable. That's the goal. Okay, and so that's what we're doing here. A and B, again, are constants, so they're not a problem. Just treat them like constants. So I've got 4x times y, which is b times this square root. I'm going to write it this way: 1 minus x squared over a squared to the 1/2 power. That is, I'm going to label this a little better. Here, I'll slide this. Well, I'll just get rid of that arrow. This is a as a function of x. So I'm just going to call it a of x. And yeah, the only variable in there is x now, like a as a function of x, because again, b and a are constant. I'm going to do my derivative, which is going to entail a product rule. So a prime of x, 4xb, the derivative of that's going to be 4b, right? It's like 4bx is maybe a better way to write that, times v, so that's going to be the 1 minus x squared over a squared to the 1/2, right? U prime v, plus uv prime. So my u is the 4bx, and the v prime is going to be 1/2 times the 1 minus x squared over a squared to the negative 1/2 times the derivative of the inside. The 1 goes to 0, and that thing I just circled is going to be negative 2x over a squared. Okay, and then I'm going to go ahead and just shrink all that so it fits on the white space here. Oops, well, I guess I could do all of it. Let's see if that gets it. Oh, that was kind of weird. Let me just get it all. There, that's better. Okay, And now this is good. I got a derivative. And once you have that derivative of your primary equation, we're really just looking for critical values, right? Places where the derivative equals 0 or does not exist. And so I'm going to factor because it's a lot easier to find those zeros that way. You could clean it up a little first if you like. I'm going to pull out a 4b. By the way, I don't know if you see this. I see two terms, one big term and another big term. That's what I'm looking at. Everything inside of each of those is multiplied. If you're like, well, there's subtraction in there, that's true, but it's inside of this power. So that's like one big factor that is multiplied on other stuff. I'm not going to worry about that for right now. So I'm going to factor out the common factor that I can get from these two bigger terms. I'm going to take out 4b for sure. And then I'm also going to take out, notice this binomial here is to two different powers, but I'm going to factor that out while I'm at it. And you might be thinking, well, why take out a 4 here when there's a 1/2? But that 1/2 can actually reduce out with that 2 because those multiply as well. So I'm going to write out front 4b, and then that 1 minus x squared over a squared factor. And the power I want to use here in like the GCF that I'm factoring out is the lesser of these two powers. So it's the negative 1/2. That's what I'm going to factor out. And you can also accomplish this if you want to write this as like a denominator square root and then give this a common denominator by multiplying by the square root over the square root. That'll work. It ends up being the same algebra, but this is a little quicker what I'm doing. And once you get good at it, a little less error prone, I think, too, a little nicer. All right, so 4b. From the first one, from the first term, we took out the 4b and we took out that factor to the negative 1/2 power. That power is 1 less than that power, which means there's still going to be this factor to the 1 power. So 1 minus x squared over a squared. And then that's, again, to the 1, so I'm not even going to put parentheses on it. That's from my first term. So here, I'll just kind of underline that to match it up. And while I'm at it, let me just kind of get rid of some of the other stuff. So the color coding works here. And then the other one, I'm going to make this, we'll go red here. And from that term, we factored out, again, the 4b, that's covered, right? And that x is still there, right? So I need that x, and then this is still there. And so we took out all of this, right? That all got taken out to that power exactly, right? That's what that is. So all that's left is the x and the negative x over a squared. So it's minus x squared. Here, I wanted to do this in purple still. Minus x squared over a squared. That's it. And that was this part in red over there. Okay. And again, the 4b times this factor is what we actually factored out. That was this. Okay. I think we're good. So now we're looking, again, this is factoring. It lets you find those zeros and, places where the derivative does not exist. This is a prime of x. And I'll just point out, like this factor right here, first of all, 4b, b's a constant. That's not going to be 0. If b is 0, it's one of those stupid rectangles. So that's not the answer we want. And then 1 minus x squared over a squared, we already had that factor in a of x, right? That's this here. That's part of here. It's right here. It's in the actual area function. It's not that either. That's not what we want. Because if that's 0, then the area is 0. That's another one of the stupid rectangles. That's where y equals 0. So this is not the answer we want. There's no answer there, though. It's this. It's this other factor that came out when we factored and had the chain rule. So we're going to take 1 minus really 2 over a squared x squared, and that's equal to 0. That's going to be the answer we want. Add that over to the other side. 1 equals 2 over a squared x squared, and then, multiply by the reciprocal, x squared equals a squared over 2, or x equals, when you square root both sides, I'm just going to say a over radical 2. If you have a red flag going off like, hey, don't forget the plus or minus, generally you're right. But again, this is an applied problem. I'm looking at the top right corner of that rectangle. It's going to have a positive x coordinate, so I'm not worried about the minus. So this is my optimal x coordinate for the area. So I'm sorry, what was that? A over radical 2? Yeah. And you can kind of tell this is all general, right? There's no difference here between x and y. One has an A with it and one has a B with it, but A and B also, there's no difference. You could turn everything sideways and it would be the same problem. So if x's optimal coordinate is going to be A over radical 2, I'm pretty sure, just right away without doing anything, that y's optimal coordinate will be B over radical 2. I'm just going to go ahead and write that. I'm that confident. But to check it, you can go back in to here and substitute in the x coordinate. And notice the b on the outside. So I guess what I'm saying is that inside should turn into 1 over 2 inside of that radical. Let's test it out. 1 minus, and then x squared. So it's going to be a squared over radical 2 squared. And then there's already an a squared on the bottom there. Here, let me get rid of that arrow. And so those reduce out. And sure enough, that's 1 minus 1/2, which is 1/2. And that's all what's inside that radical. So yes, y is going to be b over square root of 2. And you can show that. But, just thought I'd point out my prediction there and how you can kind of see it coming. So those are the optimal coordinates of the top right corner. And then with any problem anywhere in math, definitely with these optimization problems, you can ask questions a lot of different ways, and you just want to make sure that you actually answer the question that was asked. So when I go back to the book here and read it, number 24, it said, find the area of the largest rectangle that can be inscribed. So that's what I need to do, is turn that into an area now. You can go back to an area formula. I could have not even found y if I wanted to. I could have just gone to here and plugged in my x coordinate and simplified. But I kind of thought this would be easier. I knew what x and y were going to be now. So now my area is just 4xy, right? Remember, 2x times 2y. So a max, I'm going to say, equals 2a over the square root of 2 times 2b over the square root of 2. And you can see how that's going to simplify. The a and the b, so you're going to have 4ab over 2, which is going to be 2ab. Look good? I'm not sure if it's going to let me, it kind of works. Cool. So 2ab, that's my max area right there. I'm going to circle that. I like to, when I have a page full of work, I want to clearly identify my answer. No units needed here. This is a pure algebraic question. There were no units given. So obviously it would be in square units if there were any units there. But that's it.